When a student who is blind or has low vision enrolls in a UCCS class, the Disability Services Office informs the faculty member of this enrollment before the semester begins. If the faculty member has not prepared a universally designed course in advance, there will be challenges. If the instructor uses a lot of visual materials, he or she will have to find another means of communicating the lesson to a non-visual student. In the spring of 2016, Associate Professor Steve Jennings of the UCCS Geography and Environmental Studies Department had to do just that. Dr. Jennings and I met at the start of the semester to discuss some alternate methods to work with his new blind student, Q. After some discussion, we came up with two potential solutions to the many visual assignments in his class. Visual class handouts would need to be converted to tactile equivalents so that Q could perceive the materials with her hands. Fortunately, the Assistive Technology Lab houses a Braille printer embosser and a thermoform printing device, both of which I offered him as conversion tools. I also suggested that he talk to the Mechanical Engineering Department to see if he could use their 3D printer and their expertise to help create some three-dimensional manipulatives. The Braille printer, which uses pressure to create a series of raised dots representing printed language, was used to print the course syllabus for Q, so that she had a tactile printout of that document. The thermoform printer, which uses heat to raise images slightly on a page, was used to create simplified versions of the printed handouts in the class. A 3D printer was used to create three-dimensional plastic renditions of some geographical sites. Using these methods, our UCCS team of faculty, staff, and student workers created an accessible non-visual version of Dr. Jennings' geography class, and with it access for Q and other blind and low-vision students who might take this class in the future.
What looks accessible to a sighted student doesn't necessarily mean that it's easily accessible for a student with low vision.
For example, a professor gave us this printed image of geological water tables. In addition to the lack of tactile lettering, there are other challenges involved in making this diagram an accessible one.
Let's take a look at the most obvious flaws in this diagram. For starters, the dotted line that is supposed to represent the water table could be obscured by the large amounts of rock. Also, this flock of arrows is repetitive and confusing. Due to the image's low resolution, the grass near the surface water is blurred into a singular blob. Most of the image has a gray background. This gray may be just dark enough for the thermoform printer to raise it along with the rest of the lines, making the dark, important lines difficult to distinguish. Therefore, the image will need to be whitened. Finally, many of the lines lack the thickness and intensity that is standard in tactile imaging. In this case, it cannot simply be scanned in and printed off. Some sort of editing will need to take place in order to make sure that the image can be read with clarity. To do this, we have two options. One is to redraw the image in a simpler version, or edit it on the computer. For an image with so many obstacles, oftentimes it is simply easier or quicker to redraw the entire diagram than to edit it within a computer program. With some thin printer paper, tracing over the original image with an extra fine point marker is a cinch. The new lines are thick, dark, and will scan in beautifully on our high-resolution scanner. Many times we get rid of unnecessary components such as the font, lines, and arrows in the hand drawing, as accessible ones will be added via a computer. After the image has been redrawn, it looks much simpler compared to the original. Using our fast action high resolution scanner, the redrawn diagram is now saved to the Assistive Technology Lab's computers and is ready for any necessary computer editing. For the editing example, we will be showing you a different image. In order for us to get the right contrast for the final thermoform form, we need to adjust the colors on the image. This is necessary because the swell touch paper only swells on the specified black or dark lines. Knowing that, we need to make sure that black and white colors are being used correctly so that arrows and other objects can be read easily. Once the image is drawn appropriately, we need to add text that describes different parts of an image. To do this, we use a software called View Plus Braille Translator. It's as simple as copying the text you would like, translating it within the software, and pasting it in the image as Braille text. Here are the pictures of the images from start to finish. We start with an image that is not correctly fitted to the page. We then delete text and arrows so that we can modify the colors to meet the final printing requirements. Now we end up with an image that is ready to be printed and used by a student. Standard printing paper is not suitable for the thermoform printer. A special kind of paper known as swell touch paper is heat sensitive and will swell on any part of the paper that is marked with black lines. Thankfully, any black lines will cause the paper to swell, so as far as printing the diagram off initially, using a regular printer is fine. When the image has been printed onto the thermoform paper, it can now be fed through the tactile image enhancer. This produces a safe but efficient heat as it automatically feeds the image through. To ensure maximum readability, we set the dial to the highest level of swell. In just one cycle through the tactile image enhancer, the image and associated Braille lettering are now raised and accessible for the low vision student. Here is a before and after image of the printed diagram. As you can see in the second image, the black lines have completely thickened from their original flat ink printing. The student now has a completely accessible tactile diagram at their learning disposal.
I have a blind student this semester. I've been teaching for
Dr.
over
Steve
30
Jennings researched methods for creating 3D models of landforms. He reached out to the UCCS Teach Department, whose purpose is to train people to become science and math teachers. They house a 3D printer.
I was able to take data that's been collected by the U.S. Geological Survey. It's what's called pixel data, so it's small areas of the Earth's surface that have been assigned an elevation. And I've been able to use that and convert those files into a file that can be used in a 3D printer. I take the data from the USGS and I use several software programs to convert the information. Once I create the file, which has it's called an STL file, I can then send that to Corey Gavitt up in UCCS Teach, who has the 3D printer.
The final act of creating the 3D manipulative is passed on to Dr. Corey Gavitt. He is a senior instructor and master teacher within UCCS Teach. With a strong background in geology and geophysics, Dr. Gavitt is the perfect candidate to create these models. The machine is hard to miss. A noisy, whirring frame with a tool head constantly moving across a brightly colored yet still unrecognizable shape. Dr. Gavitt demonstrated the Lulzbot Mini, a 3D printer being used to create manipulatives for Q to use in her class.
This is pretty much a plug and play. It may seem complex and it may be all that, but realistically, you could order one of these, download the software, and you can be making products tomorrow.
He explained that software similar to that used in CAD/CAM work allows the creation and manipulation of STL files that Dr. Jennings sends him.
I actually do the work on it and do the measurements and create products that go together in there. So a G-code is what an Autodesk Inventor or SolidWorks or 3D CAD system, any of the programming, Google SketchUp, that would be the file that it would create. And then you would convert that into a G-code, which the program like this can then read, and then you have to put it through what's called a slicer. You can see the layering. So what a slicer does is it takes the big product picture and it talks into this frame.
On these models, these are somewhat hollow. They have a grid underneath it, so it's not all completely plastic, just that top surface.
These would be the different percentages. You can have it thicker, you can have it less solid. the dents and the lines inside. For these, we're using HIPS or ABS plastic, which is relatively inexpensive.
A model like this one can be highly educational, not just to low vision students, but to sighted students who are tactile learners.
So his visual learners are actually benefiting from this too.
Yeah.
So the manipulatives that we made, she's learning from it, and this is making it easier for her to understand. And he was kind of talking about the differences between the U-shaped valleys. So even as a seer, you can run your fingers down these versus something that a river cut. So this was a glacial valley, which gives it a broad U shape. So as he's talking about those kind of things, she can be feeling and running it over, and instead of saying in the upper left-hand quadrant of the topo map, which does her no good whatsoever.
Dr. Gavitt demonstrated how he can alter and exaggerate the 3D print of a geographic landform in order to clarify its distinctive features and make learning easier.
So the topo map that we had of Rhode Island printed out like this. And if you look at it from the side, there's not much relief. You can't see anything.
Difference.
So within the program that we have on here, I can mess with the
Exaggerate.
vertical relief, and I can exaggerate so that you can actually get an idea of what's going on in here. You can see this would be where the ocean is, and then as you're rising up from there. So there's lots of things that we can actually manipulate in here to exaggerate to give a better idea of what's going on.
The student has been proactive, but obviously there are obstacles to someone taking a class like this and not being able to see some of the representations. It's one of those things that is good for the UCCS classroom, but also has some implications for other folks around the state.
Thanks to the efforts of faculty members like Steve Jennings and Corey Gavitt, Q now has the tools she needs to learn, and with it, the opportunity to succeed. This video was created and produced by our Assistive Technology Lab team, most especially by AT Lab Assistant Carlos Garcia and Alternate Media Format Assistant Justin McConnell. Thank you to Q and Disability Services and everyone who made this film possible.